Hello everyone. I will introduce the buffer overflow attack in this video. Many people read the static application security testing report, and the buffer overflow vulnerability has been detected by the tool. They told me that the buffer overflow just caused a program crash. Is it necessary to fix it? This demo program will tell you about hackers, how to take advantage of buffer overflow attacks, and the possible harm caused by buffer overflow attacks. This is a simple login program. Let's see what the main function does. The main function only calls the function checkCredential, and the function will return 0 or non-zero. Finally, the success or failure is displayed depends on the return value. Let's see what the checkCredential function does. In order to simplify the program, and let everyone focus on buffer overflow, so the program omits the actual validation with the database or AD. Instead, directly checks hard-coded username and password in the checkCredential function. The definition of the checkCredential function has two parameters. The program copies the arguments to the local variables, compares the name and password, and what if it meets the conditions sets the flag variable to 1, otherwise returns the initial value of the flag 0. This program looks fine, but I will show you what you may not have noticed, and how hackers can exploit these unnoticed aspects. Let's test the program now. I will first test a scenario where both the username and password are incorrect. As we expect, the login fails. Next, I will test a scenario where the username is correct, but the password is incorrect. As expected, the login fails as well. I will now test a successful scenario. As we expected, the login was successful. Let's test another situation. Because the local variable is 16 bytes declared in the program, so we input a string of 16 characters. To trigger a buffer overflow in the program has generated buffer overflow. But the program is still functional. Why? Maybe someone knows why the program still runs normally after inputting 16. Don't worry, it doesn't matter. After I demonstrate the next example and detailedly explain why the next example caused the buffer overflow, most people will know why. In this example, I only added one more to cause the program to run abnormally. Why? Next, I will explain why this situation occurs. Before executing the program, we set 3 breakpoints in the program on line 24, line 9 and line 15. Then we directly execute the program. The program stops at line 24. I show you something you may not know here. I switch to the tab of the register. We are interested in the stack pointer register and instruction pointer register. I've recorded the contents of these two registers on the right. For later comparison, SP points to the stack used by the program. Let me show you what the stack has. In order to make it easier for everyone to understand, I have aligned the memory address to end with 0. At present, what I want to tell you is that the compiler will put the parameters of the function on the stack. Let's find the first parameter arg now. The address of argc is in F8 to C, and the value is 3. The next address, F830, is the address of argv. Let's see what is stored at the location pointed by the argv pointer. The argc parameter tells us that there are 3 string pointers stored in this location. The first string is stored at address 01, 15, 3F, C0. We can see that the first string is the absolute path of the program. Let's take a look at the second string. It is stored at address 01, 15, 40, 02. We can see that this value is the first argument username that was entered in the command argument field. The third string is stored at address 01, 15, 40, 08. The value you see now is the second argument password that was entered in the command argument field. We've just spent some time explaining the relationship between the parameters and the stack of the main function. I hope you are still following. If not, feel free to watch it a few more times. Next, let me introduce EIP to all of you. I switched to the disassembly window. Please pay attention to the current address in the debugger. Is it the value of EIP? Yes, EIP points to the next instruction to be executed, not the one currently being executed. Please pay attention to the values of ESP and EIP again, because I will proceed with the program. To continue executing, get into the function, and these registers will change. EIP changes because the program enters the function, while the change in ESP is because, once inside the function, the compiler pushes some data onto the stack. Currently, the cursor is hovering over to parameters, which are the addresses and values of username and password. I'll note the addresses of these two arguments on the right. We'll also note the current value of ESP on the right. The program has entered the function, so let's see what information the compiler put into the stack. Let's first calculate how much the compiler has pushed to the stack. Hex F9 F7 D4 minus hex F9 F7 540 equals hex 80, equivalent to decimal 128. So the compiler has placed 128 bytes into the stack. Whether you've learned from school, self-study through books, or online resources, all sources tell you that function arguments are placed in the stack, but how many people truly understand the meaning of this statement? Now, I'm going to show you whether the parameters are really placed in the stack. Let's have a look at this argument, arg1. Now, I'm going to show you if we can find this argument in the stack. The address of arg1 is located at the address F9 F7 CC in the stack, because I'm demonstrating this buffer overflow attack on the Windows operating system, which uses little-endian. We need to reverse the memory address when looking at it. Next, let's take a look at arg2, which is located at the address F9 F7 D0 in the stack. We can see that the address of arg2 is also in the stack, so as you've learned before, the arguments are indeed placed in the stack. Let's take a look at local variables now. Starting with the variable flag, the current setting in Visual Studio is to display in decimal. Let's change it to display in hexadecimal for easier comparison. Let's look at the flag variable in the watch window. On the first row, we can see the value and address of flag. Then, use the address of flag to compare it with the contents of the stack. You can now pause and compare the values above and below. Next, press F10 to execute and pause at the next line of the program. In Visual Studio, the places where the values of variables have changed are now highlighted in red. Next, let's take a look at the pass variable. The address of this variable is F9 F7 CO, and I'm highlighting it with the mouse. I let the program continue to execute one more line, setting every byte of the pass variable to 0. Let's continue and take a look at the next local variable, name. I highlighted the memory allocated by the compiler for name. Let the debugger execute one more line of the program, and fill every byte of name with zeros. The next line of code will copy the arg1 argument into the local variable name. Now, you can see the changes in memory. Next, let's take a look at the changes in this block of memory that the local variable pass occupies. Because the pass memory block is only 16 bytes, and arg2 has 17 bytes, which includes an additional byte for the null terminator. So we can see that the flag variable was not modified within the program, but through the buffer overflow. The flag variable has been altered. I'll let the program continue running, and because the condition isn't met, so the program jumps to the return statement at line 19. I'll switch the upper window to the register tab again. Let's confirm once again that the value of ESP has not changed. Let's switch back to the memory tab again. I'm interested in this value, and I've also noted it in the upper right corner. I'm interested in this value as well, and I've also annotated it in the upper right corner. Next, let's go back to the Register tab. To explain why I'm interested in these two values, I'll let the program run from one line to the end of the function first. Next, let's have the program exit the function and return to the main function. Now we can see that 3 register values have changed. Now, let me explain why I annotated the 2 values I mentioned earlier. Let's start by looking at the IP that changed just now and compare it to the 2 values we noted earlier. Yes, the second value we noted is indeed the function's return address. Hold on. Why is the IP value different from the one we initially annotated? This question is quite simple, and you should be able to figure it out on your own. If you can't, you can either search on Google or wait for the upcoming video, where I'll provide an explanation. Another value I mentioned being interested in is EBP. As for the function of EBP, it's not within the scope of this video's explanation. If you're interested, you can leave a comment. If there is significant interest, I'll make another video to explain this knowledge. Another question, ESP. Yes. Why does the value of ESP change after calling a function? Great question. It's because of the calling convention of the function and optimizations that lead to this result. As for those who want to delve deeper into it, you can research it on your own using Google. At the end of the video, we'll double-check whether this returned address is indeed the current address. Let's switch to the disassembly window. Finally, let me tell everyone that if this video can modify the return value flag within the stack frame, then a hacker can also modify the return address within the stack frame. You might be thinking, what's the big deal if the return address is modified? Worst case scenario, the hacker gains access to the program, and the program doesn't have any critical functionality. However, if you think that way, you're mistaken. Modifying the return address can allow a hacker to execute any program they want. Please don't underestimate the seriousness of buffer overflow. The solution to buffer overflow is quite simple. When writing data, make sure not to exceed the buffer's size. It sounds straightforward, but as programs become larger and more complex, limiting the data writing range becomes increasingly challenging. This is especially true when using libraries, where there may not be enough time to thoroughly understand the correct API usage, resulting in vulnerabilities. Of course, modern programming languages like .NET or Java no longer use pointers, which helps prevent programmers from easily causing buffer overflows. However, this doesn't mean that buffer overflows can't occur. As mentioned earlier, not understanding the proper use of APIs or using libraries that haven't undergone SAST checks, such as Fortify, can still lead to buffer overflows. That's it for today's video. If you enjoyed it, please like, subscribe, share, and turn on notifications.